So that's a really good video to exemplify what crustal subsidence and rebound are. We'll use the same video, but the beginning part of it later in the lecture to explain a little bit of the other effects. So the map below also shows the amount of uplift and of subsidence that has been seen ever since. So you can see that the northern land masses are being uplifted quite a lot, and then the surrounding areas, mostly in the oceanic lithosphere, are actually subsiding as a cause of the asthenosphere going back to the places where the ice used to be thickened at. So one of the most interesting and perhaps dramatic effects from the Ice Age was the fall and rise of sea level that accompanied the advance and the retreat of the glaciers. During the last glacial maximum, the volume of ice was about 70 million cubic kilometers, compared to our 25 million kilometers of today. So 45 million kilometers extra, nearly 3 times as much as today. Since the ice that makes up the glaciers initially came from evaporation of seawater, we know that there must have been a huge drop in sea level with glacier formation to the degree that is here said. So estimates suggest that the sea level was as much as 100 feet or 100 meters, below today's sea level. The image on the left shows the suggested coastline of the time based on that sea level change, so 100 meters below that sea level of today. But the effects on North America are probably the least amazing in terms of the coastline. For example, effects in other areas like France and Britain, they used to be connected through the English Channel. Alaska and Siberia were connected by the famous Bering Strait. The southeast of Asia was tied by dry land to the Indonesian islands. So definitely a lot of different effects from this sea level change. Conversely, if today's glaciers were to melt completely, many of the coastal areas where a great number of population actually resides, by the way, would be completely submerged by the water, which is one of the growing concerns with the observed rising temperatures that we have seen. So the two images on the right show this scenario. So you see in the North American coastal cities have mostly completely disappeared, especially here in the eastern part of the continent. The western part has seen a little bit, but the eastern part sees it the most. Florida is almost completely gone, for example. So ice sheets in North America caused some major changes in the routes of many rivers and in the size and shape of many of the valleys. The upper Mississippi River drainage basin provides a pretty good example of this. So the image on the top right shows the present day drainage, the drainage basin from the Ohio, Missouri, and Illinois rivers, which are all tributaries to the Mississippi River, which will later flow down, just like this image over here. The bottom right picture here shows what the drainage system used to be prior to the Ice Age. So the left two images also show this on a bigger scale for you to kind of envision it a little bit better. So before the Ice Age, the Missouri River actually drained onto the Hudson Bay. Now it is a major contributor to the Mississippi River. The courses of other major rivers either change paths, they enlarge, or sometimes they completely erased. For example, the Tees River, which used to be close to as big as the Mississippi in size, is now completely gone and is filled with much of the sediments from glaciation. The Great Lakes of the North America overall were created by the erosion of ice ages. So here you see that they were not there prior to glaciation. So they only appeared after or during the period of the Pleistocene epoch. So the areas where they are located, again, used to be just large lowlands where some rivers used to be and flow, again, towards the Hudson Bay. Ice sheets and alpine glaciers can act as dams to create lakes by trapping glacial meltwater and blocking the flow of rivers. So some of the resulting lakes are small and short-lived, but others can be very large and can exist for hundreds or even thousands of years. Lake Agassiz, on the image on the right, was the largest lake to form during the last ice age in North America. So about 12,000 years ago, it came into existence and it lasted about 4,500 years. As the glaciers retreated, enormous floods came about and they flowed towards the Hudson Bay. Another proglacial lake is called Lake Missoula, and it happened a little bit closer to home. It occupied much of what is northwest Montana now, and a little bit of what is the northern part of Idaho. So both of these proglacial lakes were dammed by the glacial ice, and once that glacial ice retreated, the dams failed and floods occurred. Because the ice in a glacier does not melt altogether readily, however, there were many episodes of flooding from both of these lakes. So many marks are actually left from their existence. For example, former shorelines and beaches can be observed. There are remnant lakes from where the main proglacial lakes used to be, so they're still within the landscape. And then there are some other features from the flooding as well. So examples of the remnants of Lake Agassiz are Lake Manitoba or Lake Winnipeg, just to name a couple. And then examples of the remnants from proglacial Lake Missoula is Flathead Lake, for example. Other features that can be observed from the flooding of those lakes are things like large ripples and scablands, and then sediment deposits that can be found from both of those lakes' floods. An area in eastern Washington called the Scablands shows the marks from the work done by Lake Missoula floods, as we'll see in the next slide. Other lakes formed by the cooler and wetter climate during the Ice Age are not necessarily proglacier, but are called pluvial. So these were made by precipitation fully during this time. And because of this, they're called pluvial. Pluvia means rain. So in North America, a great concentration of these pluvial lakes existed in the vast region of the Basin and Range province in Nevada and Utah. So that can be seen in this little map right here. The greatest lake within this region was Lake Bonneville in Utah, which is right here. And from this lake, the remnant lake is Sal Lake. So Lake Bonneville exceeded about 300 meters in depth, and it reached an area of over 50,000 kilometers squared. So that makes it nearly the same size as Lake Michigan today, just for your kind of visualization. So with the rock dam failure that occurred in the northernmost boundary of Lake Bonneville, many large volumes of water, or I should just say very large volumes of water, came actually gushing out of the lake or of the drainage area out of this major flood. And this flood traveled all throughout the Snake River Plain and onto the Columbia River, and eventually draining into the Pacific Ocean. And along with this flood came a lot of sediment and a lot of energy in order to carry and carve some of the landscapes that we see today throughout the Snake River Plain. The images that you can see on the slide are actually deposits from both Lake Bonneville and from Lake Missoula floods, not just deposits, but also eroded landscapes. So the large boulders, like the ones that you're seeing over here, are common in the trajectory of floods. Large ripples, like you're seeing here, these are from Lake Missoula floods that are seen near the Palouse in Washington and northern Idaho. The scablands, which you're seeing in these two pictures, are basically channels that were made by the floods as they were carving through the landscape. And then finally, the great amount of sediment that was simply carried by them. So you see in this picture on the bottom left, this is near Lewiston. So in Lewiston, which is, oh, I don't have a little map, but Lewiston is basically in the northern part of Idaho. It lies, or it's next to the Snake River, and so it received a lot of the sediments from Lake Bonneville, which are right here, and it also received a lot of the sediments from Lake Missoula. However, the Lake Missoula sediments were not from the flood direction, but they were the sediments from the slack waters of the Missoula floods. So Lake Missoula, as it was flooding, all of those floods carried a lot of energy behind, and this energy sometimes exceeded the rate at which they could make way. And so sometimes those waters would actually flow upward, they would flow uphill. And so much of these sediments are those sediments from that slack water. So we're going to talk about the history of the Ice Age now. So in the early 1800s, Ignaz Venitz and Louis Agassiz came up with this idea that much of the Northern Hemisphere landscapes were formed by the effect of glaciers, and that once these glaciers extended all the way down onto about latitude 40 north or so. By the beginning of the 20th century, geologists had actually largely determined the extent of the Ice Age glaciation, and they agreed with this idea. They also soon discovered in the sediments different organic remains and signs that the sediments had within them, and that the sediments had seen chemical weathering and soil formation in between their glaciated times. So this signified periods of warmer weather in between the periods of glaciation. So there was clear evidence that there had to have been more than one glacial advance. And these glacial advances were separated by periods of time when the climate was warmer, or if not just as warm as today's. So initially there were 4 main subdivisions made to the advance and the retreat of the glaciers, and they were named after the states that the glacial advances reached. So they were named Kansan, Nebraskan, Illinoisan, and Wisconsin. But later, with the discoveries made on the ocean floor's sediment cores, these divisions changed. So sediment cores from the ocean floor contained a much more complete record of the climate change during the Ice Age. Seafloor provides a pretty uninterrupted record of the climatic cycles, unlike the glacial record on land. And we'll look at this a little bit more on chapter 20. So this is going to tell us a little bit more about this record in the climatic cycles, which cannot be told based on the land record. Much of the land record is actually punctuated by unconformities, so times that we don't have a record for. So, different studies of the seafloor sediments showed that the glacial and interglacial cycles had occurred about every 100,000 years. So, around 20 cycles of cooling and warming were identified for the span that we call the Ice Age. Today, instead of the 4 that were originally named. So today we know that the Ice Age actually began about 2 to 3 million years ago, which means that most of these glacial stages identified before occurred during the Quaternary period, which started about 2.6 million years ago. And we are officially still within the Ice Age, as there are still glaciers on some of the Earth's landmasses. So most of the glaciation from these cycles of said Ice Age was in the Northern Hemisphere, as the Southern Hemisphere landmasses wouldn't extend that far south, except for Antarctica, obviously. So Antarctica has been in the South Pole for so long that it has seen ice sheets on it for probably close to 30 million years or so.